Hello everyone, welcome back. And in today's video, we are going to be looking at a few Pathfinder problems from fluid mechanics. So I've already made a video on a few fluid mechanics problems yesterday. So make sure you do check that out. So we'll start with an easy problem. So we have a semicircular glass tube, which is filled with water containing an air bubble, and it is sealed at the ends. Okay. If the tube is held with its plane vertical and made to move in its plane with a constant acceleration, the bubble stays aside of the highest point as shown in the figure. What can you conclude about the acceleration vector of the tube? Okay guys, so if there was no horizontal acceleration, then the bubble would be present at the top. The reason for that is the pressure towards the left and towards the right are the same. So there is no pressure gradient that will cause the bubble to move. But in our question, it's given that it displaces by an angle of theta in the clockwise direction, which basically would mean that the pressure applied by fluid on the left of the bubble must be greater, right? And for that to happen, the glass tube has to accelerate towards the right. And why is that? So let's take a fluid element to explain that. So let's take this element over here. So on this element, the fluid from the left will apply a pressure of, let's say, P1, and on the right, let's say P2. So if you want to ensure that this fluid element over here would accelerate towards the right, then we have to ensure that P1 must be greater than P2, right? That is basically if the glass tube accelerates towards the right, then the pressure on the left side of the bubble becomes greater than the right side, and hence the bubble displaces towards the right or in the clockwise sense, as shown in the figure. So firstly, it will point towards the right. And this is similar to holding a balloon in a bus or something. So initially the balloon was vertical, and as the bus starts accelerating, the balloon will turn in the direction in which it is accelerated. So it's similar to that. Okay, so now how do we find out the magnitude? And for that, we can go into the frame of the container. So let's say we are observing the bubble in the frame of the container. So now, and let's try to find out the G effective over here. The A, we have to reverse it and add it, and there is already a component of G in the downward direction. And for this to remain in equilibrium, guys, there must not be any component in the tangential or in the theta direction. Similar to how this bubble was when it was over here on top before any acceleration, right? So the G effective was equal to G. There is no component of acceleration along the tangential direction, because if there was a component, then this would again move in that particular direction. Okay, now it's fairly simple. So we just have to make sure the resultant is along the line joining to the center, and if this angle is theta, this angle would be theta. So A would simply be equal to G tan theta from trigonometry. So our answer would be BC in this case. Okay guys, so now moving on to the second problem. So we have a piece of ice tied with the help of a thread to the bottom of a cylindrical container having some amount of water. Length of the thread is so adjusted that the ice is not fully submerged. Tension force in the thread is 1 Newton. How much and in what way will the water level in the container shift when all the ice melts? Okay guys, so before we discuss the solution to the problem, I'm going to discuss a very common case, and that is basically an ice cube that is submerged in a container filled with water. Most of you guys might be familiar with this case. So in this case, what happens is when the ice completely melts, water that is obtained after melting just completely fills out this gap over here, which was the submerged volume of the ice, and hence as a result there is no increase or decrease in the water level. Let's try to understand why does that happen. So the density of ice is usually taken as 0.9 gram per centimeter cube, and the density of water is 1 gram per centimeter cube. So now we can easily say that the volume submerged divided by the total volume equals density of ice divided by the density of water. Do rho I divided by rho W, it will turn out to be 0.9. So what does that actually mean is that 90% of the ice is under water. Okay guys, so now let's say we take out the ice cube from the water and imagine that fluid is present everywhere. Imagine that there is a cavity over here that has the same volume as the ice cube. Okay, so now we have taken the ice cube outside. Now, after melting the ice cube, what is the volume of water that is formed? So let's call that VW, and that would be equal to the mass of the ice cube, because the mass of water obtained will be the same as the mass of the ice cube, right? So divided by the density of water, right? Now, mass of the ice cube, I can write as volume of the ice cube times the density of ice cube. And after carrying out this calculation, again, rho I by rho W is 0.9 times V. So again, what we get is after melting the ice cube, the water that is formed as a result occupies 0.9 times the volume. And if you guys remember, 0.9 times the volume was the volume submerged. So basically, if we pour this water, what will happen is the melted water will take up this spot, and hence as a result the water level would not rise. Okay, so how is this problem that we are going to be discussing any different? So let's figure out. So again, the tension in the string is going to be 1 Newton. Now we can write the force balance equation for the ice cube. So we can say the buoyant force must equal the weight of the ice cube plus the 1 Newton force, right? And the buoyant force is going to be the submerged volume times the density of water times G. And the weight of the ice cube is going to be the density of ice times the volume of ice times G. So from here, we can solve for the volume of ice. Okay guys, so after solving this, we obtain this relation, which basically says that the submerged volume equals 0.9 VI, which was similar to the previous case, plus an additional term of 1 by rho G. And this kind of makes sense, right? So it's basically like if you cut this string, then this would actually go up by a bit, right? It's as if we are pulling this ice cube in so that the submerged volume increased by a small amount of 1 by rho G. This is the crux of this particular problem. Okay guys, so basically from this result over here, we get that the submerged volume is slightly greater than the 0.9 VI that we obtained last case. Okay, so let's say the space I marked over here is equal to 0.9 VI. So we know that after we melt this ice over here, the water that we obtain has a volume of 0.9 VI. So that water would be enough to fill out this particular gap, right? But there is a small extra hole that is unfilled because of this 1 by rho G term over here, okay? So, and because of that, as there is not enough water to fill this spot, what will happen is the water level will come down. So that was the whole crux of this problem. So let's say I mark the new water level with red markings, and let's say it fell down by a height of h. So now we can conserve volume, right? So A delta h is the change in the volume of the water. And what would this be equal to? It will be equal to this 1 by rho G, right? Because 0.9 VA is filled by the melted water. So this would simply be equal to 1 divided by rho G, which turns out to be 2.5 times 10 power minus 3 meters. So the answer is, and that corresponds with B option. Okay guys, so moving on to the third problem. So we have an object of volume 0.5 meter cube and density 500 kg per meter cube that is glued to the flat bottom of a vessel containing water. The flat base of the object is glued to the bottom. If the maximum force that the glue can withstand is 2000 Newton, to what maximum height above the base can water be filled in the vessel so that the object is not torn apart from the base? Okay, so we have an object over here that is glued, and also it's given that the base is flat. So they're asking what's the maximum height to which we can fill water so as to make sure that the glue doesn't break. Okay. So before we discuss this problem, guys, let's just first try to understand what really is buoyancy. So let's say we have an object of any arbitrary shape and volume that is submerged completely inside a liquid. And you guys know that the buoyancy force acting on this object is equal to the volume of the object times the density of the fluid times G, right? The thing that I want to discuss is that this force arises due to the pressure difference. So let's try to mark down the pressures. So this is how the pressure diagram, the fluid pressure on the object looks like. And as you can see that the arrow size is varying, right? And that's due to the fact that the pressure increases with depth, so that this arrows over here that is pushing upwards has a higher weight, has a higher magnitude, and hence as a result, the net force is in the upward direction. Basically, buoyancy is not a one-point force which just arbitrarily starts acting on the body at some particular point. It arises due to this particular pressure difference. And it turns out that if you add up all these arrows, the magnitude turns out to be V rho G. Now you guys can try build your understanding question 19 after this discussion, because that is also based on a similar idea. Now basically okay, so now let's understand what is being asked in this problem. Okay, so most of you guys may be wondering what does height have to do with this problem, because the buoyancy force is simply going to be V rho G, right? And yeah, that's the twist of this problem. The buoyancy force isn't actually equal to V rho G in this case. It'll be slightly less, and even though I think they should have mentioned it more clearly. So if we draw the pressure forces, so the pressure forces will act at each of these points, but there won't be any fluid in between the object and the glue that is at the base. So the contribution due to those pressure forces, we actually have to negate it from the total buoyancy force. And that's the reason why buoyancy force is not equal to V rho G in this case, even though I think they should have mentioned it more clearly that there is no fluid in between the object and the surface. So that would have made it more clearer. Okay, so how do we determine the new buoyancy force? Okay guys, so what we're going to do is, as we clearly know the buoyancy force in this particular case, right? If fluid was allowed to apply a force on each and every point of this object, then we know that the buoyancy force is equal to V rho g. So all we have to simply do is subtract the contribution force that fluid applies on the base of the object from the total. Okay, and with that we'll get the buoyancy force that is required to solve this problem. Let's mark the net buoyancy force as FB1. So we know FB1 is simply equal to V times density of fluid times G. Okay, so now how do we find out the force at the base over here? So let's call it F base, and it is equal to the average pressure at the base, which we can easily find out, times the area of the base. Okay, so the average pressure at the base from fluid statics, we know that it is equal to P naught plus rho gh, right? And P naught is neglected in this case, so the average pressure is simply rho g h. Okay, so now let's draw the finalized FPD. So let's just write the net force due to the liquid as F liquid, and then we have the weight of the object, and then we have the force with which the glue pulls on the object, and let's call it F glue. We know that the maximum force with which the glue can pull on the object is 2000 Newton. So F glue must be 2000 less than 2000 Newton, and F glue from the diagram equals F liquid minus W. So these two must be less than 2000. And F liquid, as we discussed before, is equal to V rho g minus rho gh times A, right? So the moment the height of the water level becomes greater than 5 meters, the glue will fail. So the maximum height that is possible is equal to 5 meters. So the maximum height till which the water is allowed is 5 meters. That was it for this video, guys. If you have any doubts, you can comment down below. And thanks for watching.